So up to this point, I feel like a lot of what we've done has, in one sense or another, been more or less, in some sense, linear algebra. I mean, it's formalism to set up a discussion. Today, for the first time, I think I'm doing something which is genuinely geometric. All right, so what I want to talk to you about today is the so-called Frenet-Serret frame of a curve. And so Frenet-Serret, and we'll derive the so-called Frenet-Serret equations. All right. And this will take us about an hour. All right, so let me just draw a picture of what we're going to do here. Essentially, we're in 3 dimensions. All right, we're in 3 dimensions, and what we're going to do is we're going to define for a curve a set of vectors along the curve based on the particular parameterization of the curve. Now, also to keep things simple and to make them, well, geometric, we're going to assume that the curve has arc length parameterization. All right, so we're going to assume, and I'll use alpha for the curve, assume alpha from some connected subset of the reals to R3 is parametrized with respect to arc length. In other words, you could say it's unit speed, a unit speed curve. All right? And what I want to describe to you is how we can set up a frame, an orthogonal triple of vectors along the curve, which essentially describe how the curve is twisting and turning and so forth. And so the first thing you can do is, let's pick a point, say here, all right? And geometrically, you can think about, let's suppose that the parameter is increasing like this, right? So I said arc length, and I said, that's interesting because it's in some sense unique. That's not quite true, but if you pick a point on the curve and you say that's where arc length is 0, and then you say going in that direction is where arc length is positive, then that uniquely fixes an arc length function, right? That should be somewhat clear if you just think about it, right? So arc length, it's not unique, but it's close to unique, certainly up to a translation in your starting point. Now, once I pick that point, we can look at the tangent vector to that point, right? And so we can say t is equal to alpha prime of s. Now, I guess technically I should say t of s, but at times I will omit the s dependence on t, and t is a vector also. Now, what's the length of t? Well, the length of t is the magnitude of the velocity, which is what? Remember, we worked that out. That was ds ds, essentially. Well, ds dt, generally speaking. But in this context, it's ds ds, it's 1. That's by assumption, right? We're assuming that we've parameterized the curve with respect to arc length. So this t, or the so-called unit tangent vector, is already a unit vector by our assumption of the arc length parameterization. So this is the unit tangent. All right? Now, so we want to find another vector, all right, which is we can attach to the curve. Of course, we can attach these unit tangent vectors at each point along the curve, which defines, you could say this, right? T is an element of the vector fields along alpha. In the language you've been using like last class. T is a vector field along alpha, the tangent vector field. Okay, great. So what? Now, geometrically, you could think of another vector, right? If you could imagine sort of taking this curve and then fitting a circle that kind of just fits in the curve like that. See that? It's hard to see, it's blue, I know, but if you can imagine fitting this so-called osculating circle, like so it just kisses the curve like that, you could take the inward pointing normal vector like that. That would give you another vector along the curve, right? You could just like think about fitting a circle. It's easier for me to do in 2 dimensions. Like if this is, let me just go for 2-dimensional for a second here. So the tangent would be like this. I can think about fitting an osculating circle like that, right? So the normal points like this. Then you go over here. The tangent points like so. The osculating circle's over here now. So the normal points like this. So these are the so-called Frenet normals. Now, that's not actually how I'll define the Frenet normal field. There is a more elegant algebraic calculus kind of way to do it, and I'll do that now. So notice T dot T is what? That's the length of T squared, right? But what did we say about T, the unit tangent? It has length 1, so this is 1. So we can differentiate that with respect to arc length, and what does it give us? Tired of hearing the fishes. So dds of T dot T is dTds dot T plus T dot dTds. And on the other hand, that's dds of well, the number 1, which of course is 0. Right? So in short, this shows that dt ds dotted with t is equal to 0. So the derivative to the tangent, the unit tangent field, gives us a new vector field, which is everywhere perpendicular to the tangent field along the curve. So this is what motivates the following definition. The normal is equal to t prime divided by the length of t prime. So this is the unit normal. Now at this point, you realize that I have not set up the problem quite well enough yet, right? Because, well, I mean, I tried to state the problem at the start of this. We're trying to assign a frame at each point along the curve. We're trying to frame the curve, all right? And, well, okay, we got the tangent field. And I'm trying to describe how you can put the normal field by the osculating circle like that, right? But there's something, and I am assuming, all right, so first of all, there's one thing I've assumed, but I haven't stated plainly, which is that we're assuming that the vector field is moving. I mean, that the curve is not stopping, you know? We're assuming that the curve is regular. That's one assumption that we're making, right? So we're assuming that it's arc length parameters, parametrized. We're also assuming, I suppose that's that's implicit here. Unit speed curve, that means that the length of alpha prime of s is equal to 1, right? Which comes first, the chicken or the egg? I mean, if we parameterize with respect to arc length, that is a consequence. That's a theorem, right? And certainly, if that's equal to 1, it's not equal to 0, right? And if that's not equal to 0, if this is not equal to 0, it follows that alpha prime of s is not equal to 0. And this condition means that the curve is regular. Regular means that the velocity is non-zero, right? Which I would argue in some sense is just saying that the curve is genuinely one-dimensional. If the velocity of the curve is 0 everywhere, then we could come back to that example we had the other day where the curve is actually a point, which I would argue is not one-dimensional, it's zero-dimensional, if it just sits in one spot. But there's another trouble here. There's an example of a curve which is regular, but sort of defies the picture I'm drawing right now. And that's a very special case, this one. Right? What if alpha is a line? I mean, we can define the unit tangent field, no problem, right? Here it is. Whee! No problem. You pick a point, I can give you t, right? No problem. But what's the normal? What's the normal direction to a line? It's an orthogonal direction, so how many of those are there in 3 dimensions? Yeah, there's a whole sheet of them, right? I mean, if I were to try to graph it, I mean, there's like the plane perpendicular, right? The plane that takes t as the normal to the plane. Anything in here, they're all normal. How do you pick one? See, because to frame the curve, we don't need an infinity of normal vectors. We need one, right? So the case of a line confounds us. And it's not an accident that you can prove. This was the theorem I didn't prove but stated at the end of last class. One of the things was a parameterized curve is a line if and only if what? If and only if basically alpha of s is equal to p plus t times its direction vector. So if it's, I'm using s for the parameter here. So, and what can you tell me? So that's what a line looks like, parametrically speaking. What's the tangent then? The tangent vector is just straight up v, right? V is the t in this one. And what's t prime for a line? Well, in this case, it's literally alpha prime prime of s, right? But that's 0, right? So we need to rule this out. Lines are too boring for what we're doing. We need to assume that our curve is nonstop. Well, in this case, we're going to assume that the curve is arc length parameterized, which is to say it's nonstop, and also that it's nonlinear, because lines aren't going to play nice. And look here. If we were in the case of a line, we've been in trouble with this formula. It is still true that the derivative of the tangent, which in this case is the acceleration, is perpendicular to the velocity. I mean, acceleration is perpendicular to the velocity here, but it's also just the 0 vector, so it's not a special. We can't use it to build a frame, right? A frame has to be non-zero vectors, which are perpendicular, if we're going to make a basis out of them. So, okay. We're assuming then that alpha is not a line. If it's not a line, then, and it's arc length parameterized, then we know that that n is non-zero, right? And so we can divide by, well, we know that t prime is non-zero rather, so we can divide by the magnitude of t prime. What's the length of n as I've defined it here? N dot n is what? 1 over magnitude of t prime squared t prime dot t prime, right? What's t prime dot t prime? Well, no, we do not know that the derivative of the tangent has magnitude 1. We know it's non-zero because it's not a line. I mean, this is the magnitude of t prime squared upstairs as well. I mean, this and that we get 2 of them, 1 from each, right? they cancel, we get 1, right? Look at the definition. The definition of the unit normal, what I did was I took the derivative to the unit tangent and I divided by the length. That's our standard technique to create a unit vector, right? Remember Calc 3, this is how we create a unit vector. You take any vector you like, you divide by its length, it's a unit vector. That's what I did, and that's why that happened. So great, n dot n is 1. Okay, and while this may not be evident yet, it turns out that this n will point towards the center of the osculating circle. I don't think I've really proved that in here yet, but it turns out to be true, right? Because you could draw a different n to a curve in 2 dimensions. You could pick the outward pointing normal. We do this in calculus 3. If you calculate the flux through a curve, the outward pointing normal is not always the Frenet normal. Like if this curve closes like that, so this is inside, then the outward pointing normal is the Frenet normal here, but the outward pointing normal is opposite the Frenet normal at this point and also that point. I think that matters to us later, much later in the course when we study integrals around curves, so we'll get back to it when we get back to it there. But all right, so we now have 2 things. We have a tangent and we have a normal, right? So here's our t, here's our n, and great. How do you get a third vector in 3 dimensions, which is perpendicular to 2 vectors? Cross product, right? So definition, B is equal to t cross n. This is the binormal. Binormal to alpha, all right? So taken together, we have t, we have n, we have b. These are vector fields along the curve alpha. And I claim that they form a frame. They have length 1, and they're perpendicular, right? How do I know that t and n are perpendicular? Well, that's how we constructed. N is what? N is literally t prime divided by a number, right? So they're parallel. That number is positive, in fact, right? Magnitude t prime. So certainly t dot n is 0. You know, certainly t dot b is 0, right? And certainly n dot b is 0. How do I know the last? I mean, as Audric told me, construct it with a cross product. Well, we know cross products are perpendicular to both of the things that they cross, right? The dot product of b with t or b with n are both 0 by construction of the cross product, right? Now, my claim is that TNB is a right-handed triple, which means that if we calculate cross products of Tn and b, it behaves just the same as like cross products of x hat, y hat, and z hat, or I, j, and k for you guys, right? So I guess you guys are aware of the identity. Let me write it down right here. There's different ways of writing it. Let me write it the way I want. Hey, where'd you go? Yeah, okay, fine. So this is the triple product identity, A dot B cross C. Equal to B dot C cross A, which is equal to C dot A cross B. So this is the cyclicity of the triple product identity. And I just wanted to take a minute of class here to show you, I claimed that if you know the cross product, if you set B is equal to T cross N, my claim to you is that's going to sort of, well, let me draw a picture here. You guys know the story. I, J, K, the usual notation, right? So for example, I hat cross J is K hat, right? And likewise, how's it go? J cross K is I hat, right? K cross I is J hat, right? So my claim to you is the fact that we set T cross N equal to B, that will, by the same patterns, force N cross B to be T and B cross T to be N. But don't take my word for it. We can prove it from the cyclicity of the trace. Check it out. So like, let's see here. And I actually kind of like this little discussion as sort of a warm-up for what we're about to do. Okay, so is it clear that these form a basis for 3 dimensions? If you pick vectors at a point, you can build any vector as a linear combination of T, N, and B, right? If that point is a point on the curve, right? So if I think about the vector, let's say N cross B, I can write that as N cross B dot T in the T direction plus N cross B dot N in the N direction plus N cross B dot B in the B direction. Do you understand why I'm saying this? Why can I do that? It's the same thing as if I've got a vector, right? In the usual notation, vector V, I can say that's V dot I hat, right? Plus V dot J hat, plus V dot K hat, in the same way. I can expand a vector as in terms of dot products with the basis. I do need something for that to be true. I need that the basis is orthonormal. They need to be perpendicular in length 1, but T, N, and B are exactly that, right? So, and more than that, what else do we know? Well, hey, this and this are what? 0, right? Because the cross product is perpendicular to B and N, right? That cross product. And so we're just left with this, right? So at this point, I'll use the cyclicity. So this is the same as what? This is B, first of all, commutative property. This is T dot N cross B, right? Because the dot product's commutative. Now I'm going to use this property up here. So I can say that that is N dotted with B cross T. Well, that's not especially nice, because I don't know what B cross T is either. But one more time, this is B dotted with T cross N. But what is T cross N? By definition, T cross N is B, right? This is B. So we got B dot B, T. What's B dot B? Well, so what's the magnitude of the cross product of 2 orthogonal unit vectors? Not 0, no. B is the magnitude of T, magnitude of N, sine of the angle between them. What's the angle between 90? So that is 1 times 1 times 1, 1. B is a unit vector. So B dot B is 1, and what do we get? We get T, which is what I claimed on the basis of pattern matching up here. So last time I just flippantly claimed that if you tell me the cross product of the first one and the second one is the third one, it automatically implies the other cross products follow in suit. This is how you prove that. That's with the cyclicity of the trace. Okay, now that's a digression. This whole board I just went through is a digression, but it's a digression which I intend to. I think it should help us understand the next arc of the argument. All right. So one thing I need to define, and we could have defined this already, but I just didn't yet. And so here it is. Definition. Curvature of alpha is denoted by kappa, and that is equal to the magnitude of dt ds. All right? Curvature. So now that we know that, we can go back, right? And you guys tell me. Let's see here. What is n equal to? Well, what's t prime equal to? So we had, before we had n is t prime over the magnitude of t prime, right? But what's that tell us? That tells us that dt ds is equal to the magnitude of dt ds, right, times n. But what is the magnitude of dt ds? It's the curvature, right? This is kappa n. And that is one of the Frenet equations. So I'll capture it again here. Therefore, dt ds is equal to kappa n. That formula continues to make sense for lines with the understanding that the curvature of a line is what? Should be like a line isn't curved, right? So we would say the curvature of a line is 0. And indeed, if the line is arc length parametrized, the second derivative of the parameterization is 0. So this is consistent with that because like dt ds is actually alpha prime prime in this context. Okay, so that is one of the Frenet equations. So here's the theorem for nonlinear unit speed alpha with Frenet frame, T and B, there exists function tau of arc length, all right, such that let's see here, dt ds is equal to kappa n, dn ds and db ds So dBds is actually minus tau n. And the NDS is, oh man, I never remember these stupid things. Minus kappa tau. Not tau, minus kappa t. Either plus or minus, man, my stupid memory. Plus tau b. Now this tau is called the torsion. All right. So this is a theorem, and you notice that we've already proved the first third of it, right? Because we already have that dTds is kappa n. There's nothing, that's already done, right? And we've already shown that TNB form a frame, so that's already done, right? So what remains is to prove that dNds and dBds are as advertised, all right? So how do you capture what dNds is? Well, actually a lot like what I did over here. So what we're going to do is we're going to look at the derivative dNds, which fits into the category of what we were talking about last time. It's a vector field along a curve, right? Because we're differentiating a vector along the curve. And so like, here it is. So we know that make sure I do the right one first. Okay, so I'll look at B prime first. So B prime, and so rather than, I'm going to use T prime, N prime, and B prime here because it's easier to write, obviously, you know. But B prime, we can write as B prime dot T in the T direction plus B prime dot N in the N direction plus B prime dot B in the B direction. So what I'm doing is I'm expanding the derivative of the binormal into its tangential, normal, and binormal components. I want to argue that both the binormal and the tangential parts are 0. All right? Now, one of those is easy. Observe, B dot B is what? B dot B is 1, because B is a unit vector. So differentiating gives me B prime dot B plus B dot B prime equal to 0, which implies that B prime dot B is also equal to 0. So, 0. Now I want to get my pause on the T component. This is junk right here. That was supposed to be what? N. Thank you. Okay, so we know that, let's see here. B dot T is equal to 0, right? I have to be careful here because, I mean, there's lots of different things you could look at. And I have had more complicated, longer proofs of this in the past, which were not incorrect. They didn't get to the point as quickly. I think this is the fastest path. All right? So here we go. B dot T is 0. Differentiate. What do you get? Differentiate this. We have B prime dot T, which is what I'm after, right? Plus B dot T prime equals to 0. But what is t prime? So that's minus b dot t prime, right? What was t prime? T prime is kappa n. So what's b dot n? So you've got minus kappa b dot n. What's b dot n? Well, b dot n is 0. So that shows that this piece is 0, right? All we're left is this guy. Okay? So with that, we make a definition. Definition. Tau is equal to minus dB ds dotted with n. This is the torsion of the curve. And with that definition, we have equation 3. Right? So now b prime is minus torsion times n. So does there exist a function? Yes, because this right here is exactly a function of arc length, right? You actually calculate this dot product, all you're left with is functions of arc length, which is itself a function of arc length. And then finally, we have one left to do, right? So the middle equation, we can attack that now. So notice n prime is n prime dot t plus n prime dot n plus n prime dot b. Once again, we're using the fact that T and B form a basis for the vectors at the curve, at the point on the curve we're looking at. And once again, n dot n is what? 1, which implies that n prime dot n plus n dot n prime equals to 0. So therefore, n prime dot n equals to 0. So that piece is gone. Right? And let's see here, how about the other pieces? Well, we know that n dot t equals to 0, right? N dot t equal to 0, differentiate that, what happens? N prime dot t plus n dot t prime equal to 0, right? So what's that tell me? That tells me that n prime dot t is equal to minus n dot t prime. What was t prime, though? Is what? T kappa n, right, kappa n. So we get the kappa pulls out, it's a number. I mean, it's a scalar function generally, but pulls out, we get n dot n, which is 1. So this gives us n prime dot t is minus kappa. All right. So n prime dot t is apparently minus kappa. And then, of course, one last derivative to do here, n dot b is equal to 0, right? Differentiate that. What do you get? N prime dot b plus n dot b prime equal to 0, which tells me that n prime dot b is equal to minus n dot b prime. But what was b prime? Right. Yeah, negative tau n, right? So this minus and that minus cancel, and n dot n is 1. This is tau. And so there you have it. This right here works out to tau. And that's exactly the second Frenet-Serret equation over there. Okay, so, uh-oh. What did I do? Okay. So I think it's healthy for us at this point to work out an example. Let's do that. So we'll look at the example of a helix. And here it is. Alpha of S is equal to R cosine Ks, comma R sine Ks, MKS, where R and M, we'll assume are positive constants, and this K I define to be 1 over the square root of R squared plus M squared. All right? So given our current technology, in order to make use of what we have, I better know that this is unit speed parameterized, right? So let's calculate the derivative. And Audric, you'll get your wish. I'm not going to use the U1, U2, U3 notation. I'm just going to use the bracket notation here. So let's see here. We got minus R K sine Ks, R K cosine Ks, MK. And what's the length of alpha prime of S? Yeah, square root of R squared K squared sine squared Ks plus R squared K squared cosine squared Ks plus M squared K squared. What's that work out to? So we can just take these guys together and convert it to R squared K squared plus M squared K squared. So we could factor the K squared out, right? Okay. Oh, I'm sorry, that's horrible. K times the square root of R squared plus M squared, which is just what? Oh, K was 1 over the square root of that. So lo and behold, we've got square root of R squared plus M squared over the square root of R squared plus M squared. So you know what? Good news. This is in fact, arc length parameterized helix. All right. So now we're well within our rights to calculate the Frenet frame as I've laid it out so far. In fact, we already have one of them, right? This right here is the unit tangent, right here, right? So the unit tangent is just the velocity vector in this case. There it is, right there. So next up, well, actually, if you don't mind, I really would like to erase this because it's not especially interesting and it's going to be in the way. You're fine. Just warning you what's coming. We good? Now we're good? Okay. So what's T prime? T prime is minus r k squared cosine ks minus r k squared sine ks. And that's a constant, so derivative is 0. Now, I would point out that you can write that as r squared k squared, rather r k squared, rather. R k squared times the vector minus cosine minus sine 0. This is manifestly a unit vector. Right? That's a unit vector. Its length is 1 because it's got cosine and sine for components. That is a unit vector. It follows that the magnitude of T prime is literally r k squared. Because any vector, we can do what? We can write it as magnitude times unit vector, right? So if that's the unit vector, that's the magnitude. And the magnitude of T prime is what? It's called the curvature, right? Because we're using arc length parameterization. So this tells me that the curvature for the helix is in fact r divided by r squared plus m squared. There you go. That's the curvature of a helix, parameterized as we have it. Now what's left? We've got t. By the way, this unit vector is n. N is in fact, minus cosine ks minus sine ks 0. That is the unit normal right there. There it is. So how do we calculate the binormal? By definition, t cross n, right? So you have to take the cross product of this and that. All right? Uh-huh. Well, k is 1 over square root of, so when I square k, I get the r squared plus m squared, and the r just stays up top. Mm-hmm. Okay, cool. Yeah, however you guys want to calculate the cross product. I'm gonna do it old school. Now I'm just gonna look at it. So the z comes from this times that minus that times this. So I start with mk sine ks. And then to get the y, I do z cross x. So then I get minus mk cosine ks. And then to get the z component, I do this one times that one, which gives me a plus sine squared plus cosine squared. So the cosine squared plus sine squared gives me 1. I get rk. Yep. Now, well, I don't think so. If you take the dot product of this and that, you get 0. Because you notice this has got minus, minus. I need a flippity-floppity of signs over here, otherwise I'm not going to get it. So like dot product of this and that gives me a minus and a plus. Minus, plus, same term, sine, cosine, cosine, sine, 0. Also, this dot that conspires to give me minus sine squared, minus cosine squared, same coefficient, r k squared, m. Over here, r k squared m. So we get minus 1 from the sine squared plus cosine squared with minus, and then a 1 here. In other words, dot product of b with t and b with n are both 0. So I think my answer is right. I think the minus sign you're thinking of, you got to, in the determinate calculation, you like lost one of your minuses. But if it's any consolation, half the time I do the calculation, I make the same sign error you're talking about, and then I find it when I take the dot products. So. So there's the binormal, right? Now, what's the torsion? How do we calculate torsion? In our current technology, we have to calculate b prime, right? So db ds is, what do you got here? You got m k squared sine ks m k squared cosine ks, and the derivative of the last term is 0. And I have to do what? I have to take dbds dot what? Dot with the normal, right? To calculate the torsion. Wasn't that our definition? dbds dot n. That actually gives me minus the torsion, right? So let's see here. dbds dot n, what is that? Well, I'll add the minus once we're done with this calculation. N is right here, right? So what happens? Oh, I can't do math. What's the derivative sign? Cosine, maybe, right? Yeah. Maya, I blame you. I'm just playing. I said I blame you. I made a differentiation mistake. It must be your fault. You asked me a question, so I'm just kidding. I encourage questions. It's actually very good. So derivative of cosine is minus sine, right? So it's sine. I don't know what happened to me there. Anyway, that's good because when we take the dot product, right, of dbds and n, this multiplies by that. You get what? You get a minus cosine squared, you get a minus sine squared. Those add together to give you 1. What you're left with is minus m k squared. Now keep in mind that this is not the torsion. The torsion is minus that, right? So this implies that the torsion is m over r squared plus m squared. So there you go. This is the curvature for a helix, and that's the torsion for a right circular helix. It's fun to look at special cases, right? What happens when the helix has radius go to infinity? If the radius goes to infinity and the m is fixed at a constant, the curvature goes to 0, right? Because r squared wins. And likewise, the torsion goes to 0 because r squared wins, right? Likewise, if we think about m going to 0, well, I don't know what exactly happens there. Anyway, what happens if m equals to 0 and the radius is not non-zero? So if m equals to 0, that's actually a very interesting case. What happens there? We get curvature, 1 over r, and we get torsion equal to 0. And of course, when m equals to 0, the helix is actually a what? No. I mean, r going to infinity would be straight line, kind of. There's two different things you could think about as a limiting case for straight line for the helix. The one you could think about, I mean this, so you could think about like tightening the helix, like letting r go to 0 and like it be kind of like a stretched out, that's kind of like a line, right? The other thing I could do is make r go to infinity, and then that would also be kind of like a line. But this is definitely just a circle. That's not a limiting case, that's just true, right? M equal to 0 gives you a circle when you look at the formula here, because you just get sine and cosine, and it just sits in the z equals 0 plane. It's straight up a unit. It's a circle with radius r. So lots of things to learn about the Frenet frame just from this one example. The torsion being non-zero speaks to the fact that the curve is lifting off its infinitesimal plane of motion, right? And the curvature being non-zero speaks to the fact that the normal is changing direction. In fact, if you go back to the Frenet-Serret equations, these tell a story, right? And the story the Frenet-Serret equations tell is the story of how, the frame evolves with time, right? What these equations are saying is that if the curvature is non-zero, as you go along the curve, the tangent vector is bending into the normal direction. So this is the normal direction. This is the tangent direction at that point, right? The curvature here is positive. If you can think about in your mind's eye that just evolving just a little bit over to here, what's happening is that the unit tangent is getting twisted down into the normal direction, right? The normal also changes in a more complicated way up here. So the normal, yes, indeed, it starts to go into the minus the tangent direction a little bit, doesn't it? And if this curve is genuinely as advertised, if it's genuinely just in the board, it turns out that the torsion is 0, so there's nothing contributing to the B. So we're going to take a little break, and then I'll come back. I have another about half hour of interesting theorems and results to share with you about this. We'll talk about what we do, probably another hour actually. I'll talk about what we do when we parameterize with respect to something other than arc length. Then we'll actually make contact with formulas from physics and such. So, all right. So I'll stop here for the moment. Take like a 10-minute break.